a pleasure to be here tonight. I'm going to take you through two projects I've been working on for the past year or so that essentially deal with new mark-making systems in data visualization. The first project is called Halo, and it essentially tries to answer the question of what does a post-data world look like, where the modes of interaction with data and data signaling devices follows naturally after the widespread acceptance of data language, but also the widespread understanding of data language in society. So this is the conceptual realm that we've been occupying in designing a new type of visualization system, which is essentially a three-dimensional intelligent digital object whose transformational characteristics, what it does, how it transforms in time and space, is entirely driven by the data being piped into the system. The system is composed of 6 primary axes and 6 secondary and tertiary axes. Each of these axes streams a live data set, live separate data set. So what I'll do is I'll take you through the basics of the system so that you understand what I'm talking about, and then show you 3 specific use case examples. The primary and the single most important axis in Halo is size, because it is the most visually noticeable thing. It has the highest visual value. And as I showed you in the previous video, Halo increases size by simply adding numbers of rings. What's cool about that is that you can engineer precision with regard to incremental variation that exists between 2 different halos of 2 different values. Secondly, color is probably just as important because of the visual impact. We have a number of different presets of colors in Halo, but typically colors range from cool colors like blues to warm colors such as yellows, and then of course continuous variation in between those 2 extremes. What's interesting about that is that it allows you to categorize quantitative variation, which is actually quite useful for a lot of data sets, even if you don't necessarily use it. Complexity is the amplitude of the sine waves of the individual circles, the individual rings rather. On the left-hand side, you see a nearly perfectly smooth halo. Does that show up? Can you bring these lights down here? And on the right-hand side, you see a highly complex halo. Like size, complexity's visual value is actually quite high, in that you can tell the difference between 2 halos of relatively small values that have relatively small complexity value differences. No, it just crashed. Fuck. Okay, the thing to do is exit this screen and then just reload it, replay it. Don't turn it off, just exit this and replay. Oh no, forget about it. No, it's cool, it's cool. Okay, next axis, movement. This is the one that people like the most. Movement is simply the degree of symmetry of the underlying generative animation. On the left-hand side, you see a perfectly symmetrical halo. On the right-hand side, you see a highly asymmetrical halo. We tend to reserve movement for any kind of data that has to signal deviation from normality. So in particular, if it's a health application, any kind of very dangerous metric threshold, for example. And the reason that is because, as you notice here, is that when you have very high movement, that's the highest value that exists, but there is continuous variation in movement as well. When you have very high values of movement, it becomes very difficult to judge other axes like size, for example. Although color is, of course, not affected. I'm worried about pressing it twice because I think it'll go twice ahead. All right, so there's a long delay. What I'll do is try to remember that. Speed is the most obvious axis. It's just simply the speed of animation of the underlying generative structure itself. On the left-hand side, a nearly static halo. On the right-hand side, a relatively fast-moving halo. We tend to use speed for any kind of data with regard to signaling rate of change and increases or decreases of rate of change. We have the ability to play back halos within any kind of system, which means that you can actually determine changes of rate of change over periods of time as well. The last axis is, oh Christ, this is going to be really annoying, is brightness. And that's just simply the degree of opacity of the underlying rings themselves. On the left-hand side, a nearly invisible halo. On the right-hand side, a bright halo. Those are the 6 main axes. In addition to these 6, there are 6 secondary and tertiary axes. I'm not going to go through all of them because it would take forever, but I am going to show you specific use case examples of some of those tertiary axes and how they come into play and why they're important. The first application I'm going to show you is a platform that we're building for iOS. That's a combination of the Apple Watch and the iPhone. And what it essentially does is it takes live sensor data from the watch and from HealthKit, and it represents all of that information, X number of axes, I'll go through the axes in a minute, X number of axes into a singular composite representation of personal self. The idea here is that instead of looking at 5 to 7, 8, whatever individual graphs in HealthKit, you simply have a halo that you grow every single day, and the dynamics, the transformational dynamics of the halo are fed by your personal data. And essentially, it is a visual representation of how you use your body and how you live your day from a health perspective. Our partner for this project is the Mayo Clinic in the US, which I think, although I really should know this, I think it's the largest private research clinic in the world. They're interested in this is one, from a wearables point of view. Can we develop a system that uses an entirely different language that allows people to understand who they are without having to go through complex graphs, which, to be perfectly honest, most people can barely read an XY graph. And then second, what they're interested in is remote monitoring. So for example, if you have thousands of people on this kind of system, you can actually monitor them real time, but remotely. So have one doctor monitoring 100 or say 200 individuals at any one given time. The system itself is, as a first launch, is relatively simple. It only uses, I think it's 4 axes. So in the morning, you get a halo that looks like this. Once you put your watch on, the halo expands and then increases in size by adding rings with increases in steps, distance cycled, flights climbed, etc. You get a delineation threshold line for 10,000, and of course the halo keeps growing more after that. The halo increases in complexity with spikes in heart rate, and then it gets smooth if you have lower heart rate. That's approximate representation of heart rate. And then the halo starts glowing and changing in color if you maintain a threshold heart rate for a certain period of time. So the brighter the color, the higher the heart rate. So yellow is in the 160 zone. And then the halo fills up. It takes half an hour of elevated heart rate to fill up an entire halo. And that's the daily recommended, essentially, half an hour. You get these pulsating waves with incremental changes in activity, so if you're increasing activity over time. And then the last axis is if you haven't stood for a period of time, your halo goes asymmetrical, and then as soon as you've had at least 20 steps in an hour, it goes back to symmetrical. Very simple system, and the first launch is only 4 axes because the idea here is that because it is a composite system, users will be able to tack on additional axes as they see fit, with our recommendations, of course, as in, like, it's not a free-for-all. You can't just simply add things however you see fit. The cool idea here about this is that, which I'm not going to show, is what Mayo Clinic is particularly interested in, is that with HealthKit, because there are so many possible data streams that you can pipe into the platform itself, and with individuals that have specific ailments like diabetes, we will be able to generate ailment-specific halo systems. So individuals that have diabetes will have a different looking halo than individuals that don't. And then that difference is essentially that tacked on additional axis. With this type of very simple system, you can generate what are termed health phenotypes, which is essentially a visual differentiation of people based on how they use their bodies. And the most extreme cases are these two, for example. On the left-hand side, you have a highly active individual, very large halo, entirely yellow, which means they've gotten at least that half hour a day, fast-moving, high complexity, and symmetrical, versus the person on the right-hand side who is relatively sedentary. You see that pronounced asymmetry. It's relatively small and blue. So these are the two extremes, but of course anything in between is also possible. So in addition to the extremes, these types of phenotypes, these characterizations of human beings, you can also characterize nuanced variation between individuals. These are two individuals that are both highly active. The person on the left-hand side, substantially larger halo because they have more overall activity in terms of steps. It's more bright, although the brightness only fills up about half, so that's an elevated heart rate of about 170 for about 15 minutes a day. Compare that to a person on the right who's also highly active. They have a fully orangey yellow colored halo, so they still get half an hour of exercise a day, but their heart rate threshold is lower, which means the intensity of their exercise is not as high. And a lot of people think that they're active with regard to like how they use their bodies, but at the same time too, what they're missing out is this issue of intensity. So you may be quite active, but in fact, you're not actually doing that much good for your heart. And that's personified in this case example. On the left-hand side, you have a highly active person. They have about maybe 20 some odd thousand steps, so the halo is extremely large. But it's, for the most part, bluish purple, which means they've never actually elevated their heart rate over, I would say, the 90 BPM zone. So for example, the person on the left could be a mailman that is constantly on their feet, constantly doing some sort of activity, but the activity is relatively low intensity activity. Compare that to the person on the right, who, although the halo was smaller and the halo was asymmetrical, so they are spending significant periods of the day being relatively inactive, they've at least gotten a certain portion of their halo filled up, so I would say about maybe 10 minutes of a higher heart rate threshold, which means the person on the right is actually approaching a healthier state than the person on the left. The interface itself includes a number of numeric indicators to allow the individual to understand what they're seeing in addition to the halo itself, which includes resting heart rate, exercise average heart rate, exercise peaks, which is what the color representation is, and then exercise duration as well. So once you've reached the 30 minutes, that's the general threshold to fill up the entire halo. And again, the total number of steps, which is the most common metric that a lot of wearables give you. And that's the one that people tend to focus on the most, but it's really, it's telling, but at the same time too, it's like a very low level of information quality. And here, again, you see the difference between these two individuals. These are real individuals, and these are the real metrics for these types of individuals. Both extremely active, but the qualitative nature of the activity is hugely divergent. We have a number of different modes in the halo system. This is the phone itself. This is what we term the live halo mode. So this is the cumulative halo that you build up every single day. So you get a new halo, you have to build up the halo, and how it changes is dependent on how you use your body. So the cumulative aspect of it, though, means that if you want to understand what happened 2 hours ago, of course that's not possible unless you happen to have looked at your halo and remember what it looked like and then compare it to the present state. So in addition to this state, we have what's termed the energy map. And what this is, these are the two same people that you saw previously. All this is a time stratification. So you are given a ring, one per every 10 minutes, and then the color of the ring is a representation of the heart rate at that period of sampling. And what you see is that, again, as with the previous example that I showed you, the person on the left has a primarily, almost entirely blue halo. You see there are like very faint purple bands of 2. I think there were 2 there? Yeah, there were 2. So that represents at least some level of elevated heart rate, but compare that to the person on the right where you see that pronounced and very thick yellow band of at least 30 some odd minutes, was it 37 minutes of high activity, and then 2 additional bands, one is red and one is purple at a later time to show that massive divergence between these two individuals in terms of lifestyle. The thing about the use of this type of system, in addition to the live halo, as we term it, is that the distribution and how many of those yellow bands, if you are exercising throughout the day, also determines the phenotypic nature of how you use your body. So instead of just having one band, you should really be encouraged to have at least 3 or 4, etc. That way you spread out the exercise throughout the day. Even though you may have a total of, say, an hour of exercise, that is still better than doing it all at once. So again, the level of specificity is quite deep. I'll leave that for now. The second application is also a health-related application, but it's entirely different. It's a clinical setting. We are building a halo system for intrapartum fetal heart rate monitoring during the birthing process. During the birthing process, the doctor essentially sees this, and this is a continuous stream, so it's animated, which is essentially 2 bits of information. One is the fetus's heart rate, which is the, what color is that? Purple line up top there. And then the other bit of information is the mother's contraction cycle, which is in green there. Without going into too much detail, the reason you have to have both, as opposed to just simply looking at the fetus's heart rate, is that typically what happens with a contraction cycle in the mother, the fetus's heart rate depresses in what's termed a deceleration event. So the heart rate simply goes down, and it goes down quite fast and quite substantial. As long as those two are timed and synced, then the state of the fetus is considered safe, even though it may seem like the fetus is going into distress. But if you get a deceleration event that occurs before the contraction cycle, or well after the contraction cycle, or is maintained after the contraction cycle, then the state of the fetus is in distress, and which, if maintained, can result in brain damage and then, in some extreme cases, death as well. So this is the view that the doctor sees in terms of data output. But to aid the doctor with regard to understanding the state of the fetus, and what you're looking at here from a physician's point of view is you're looking at pattern recognition. So you want absolute values in one versus the other, and then matching those up to understand what the level of sync between the two is. But at the same time, too, you want to understand the pattern overall, what came before, what's coming after, with regard to being able to predict the state of the fetus to come. So in addition to this, doctors essentially have to construct this kind of data table in their head. So every single one of these entries is a state of fetus based on that previous information that I showed you, based on the components, the basic components of the fetus's heart rate and the mother's contraction cycle, but also qualitatively labeling the quantitative data in this manner to actually simplify it. This has to be done in the doctor's head, so you can imagine how difficult this is. Although it may seem complicated, it is actually simpler than what I showed you previous, which is a bit of a paradox because you think the previous output's simpler. Without going into too much detail, blue-green is a safe zone. Yellow-orange is an intermediary state. It's termed an evolution state. It's actually quite critical because most fetuses occupy a yellow-orange zone. And then red is a danger zone, which obviously is highly undesirable. So what we did, and this, although this is being used as a simplification tool for quite some time now, the rate of fidelity, even amongst seasoned practitioners, is so low that what we're doing in conjunction with researchers who are advising with regard to thresholds and whatnot, is we've developed turn on the lights again, just keep them down. We've developed a halo system based on the table that I just showed you, but that is fed by the raw data of the first slide that I showed you. So without going into too much detail, again, what you essentially want to see is a state as the one on the upper left. The halo is large, but not too big. That represents basal heart rate, essentially. The halo is perfectly symmetrical, which represents heart rate variation, which is pretty much the most critical aspect. And the level of complexity is kind of in the medium zone, which represents the balance between accelerations and decelerations. Compare that to the one on the lower right, which is an extreme danger zone. A fetus in the lower right is essentially about to die. So you see that massive visual divergence, and you see that differentiation, which allows you to very quickly code the state of a fetus. But in addition to those extremes, as I mentioned, most fetuses actually occupy the in-between states. And the in-between states are critical because the combination of data being piped in has to be read from a meta perspective, so that allows you to understand the overall state of the fetus. So the combination of axes, but at the same time, too, the individual combinations are critical. So in this case, the halo is read as an overall from a meta perspective. What does it look like overall? But then at the same time, too, you have to be able to, as a physician, read the individual axes. So for example, a large smooth halo is more dangerous than a small complex halo. And it's these evolution states that are critical because depending on the combination of axes, you'll be able to predict what comes next. And as I mentioned, this information, this is the information for the fetus alone. So this is the fetus's heart rate information. This information has to be coupled with the mother's contraction cycle. And this is where our tertiary axes come into play. So you'll see the mother's contraction cycle is represented as a propagating wave that comes out, essentially. The number of those lines and how thick and bright they are represents the intensity of the contraction. And again, this is entirely fed by data. It's purely passive. And then how long it takes to propagate, that's the duration of the contraction. And then, of course, how often it occurs is the periodicity. And what you'll notice is that with every contraction wave, the halo smooths out. That represents a deceleration event, and then it bounces back. So as long as that kind of recurrent pattern occurs, then the state of the fetus is considered safe. But you'll notice that in this scenario, as it just pops up now, there's the contraction wave. The deceleration event, the smoothing of the halo, starts maintaining itself. So the heart rate is not bouncing back, and that in this scenario, the halo starts turning red because it maintains the redness, the smoothness rather. And then if you continue to watch it, it would start getting more and more wobbly. So this system is designed from that two-pronged perspective where it is a meta view, a meta visual analysis, essentially, but at the same time, too, also has to be read from its components and be able to be read as components as well. The last application I'll show you with for Halo is actually the first one that we did, simply because this is where we found the most data. And it is a composite representation of gameplay for the online game League of Legends. I'm sure some of you have heard of it at least. It's, I think, still the most popular game. Something like 60 million people play it on a regular basis. But what's cool about League of Legends from our perspective is that because it is played online, every time you play it, all the gameplay information gets stored. And of course, because of the nature of the play, it's a team play scenario, typically. And because it's so deep and complex, players are utterly obsessed with their stats. And they have to be, because it's not a free-for-all. You don't just go on, form a team, and then expect to win. It's actually quite difficult. So there are loads of sites that cater to players with regard to statistics, so that they understand themselves, they understand the people that they're playing with on the team, and then, of course, they understand their opponents, too. So it's actually quite complex in that sense. But before we came along, there was no composite representation of player identity as a visual or as a composite data representation. And that's essentially what we did with the Halo system. You'll notice that the Halo looks different. We have the ability to, I guess for want of a better term, skin the Halo so that the visuals match, the data representation visuals match the context, and in this case, the gameplay context. For those of you that don't know LOL, essentially players play multiple characters within the game itself called champions. They also play multiple roles. So this is essentially the primary page for one player. They're called summoners. And this player plays 18 different champions. So as the person toggles through the different champions that they've played, you see the variation changes within the Halo itself. The changes that are shown represent 6 different statistics. Some of them are primary statistics with regard to how well they win. For example, that was fantastic. But then other ones, what they do in combination, create I guess for want of a better term, a data signature of how the person plays those particular characters, which allows you to very then quickly understand how well the other people on your team are and what are their strengths and weaknesses with regard to the particular characters that they play in the game. I actually don't play the game. So in addition to this page, which includes all of the means by which to understand how to read the Halo system, the page that's actually probably even more useful is the team formation page. So what happens is that while the game loads, players form in the queue. They determine who they're going to be playing with on their team, so it's team formation, essentially. And then while they're doing that, they assign the individual roles they're going to play, because there are multiple roles in the game as well. And then which characters they're going to play for those particular roles, which champions they're going to assign to the particular role. The idea here is that it's not a free-for-all. You don't get to simply choose whatever the hell you want and then assume you're going to win. You have to negotiate with regard to the roles that you're going to play. So you don't want to double up or triple up on the exact same type of role, or pick characters that have too much overlap, because then strengths and weaknesses are not balanced out, and from a strategic point of view, you're bound to lose. And one of the players always has to play a support, and the visual signature of a support is always smooth because of the nature of the gameplay itself, as shown in the second last one there. So this allows you to very quickly create a heterogeneous team without having to make, although you still look at all the individual stats too if you want to reconfirm whatever components are a part of the system, but it allows you to very quickly decide on decision making. I should also point out that in the Mayo Clinic example, although I haven't shown it because we're not contractually allowed to, but what they're really interested in, as I mentioned, is remote viewing and remote monitoring of patients. So instead of this being a team formation, imagine one doctor remotely, wherever it may be, simply monitoring patients and then simply toggling between individual patients as represented as halos. And of course, it's fully interactive, so once you tap on a halo, you can bring up the entire patient's history to understand their state. And we also have the ability to play back halos, which means that you can actually map the trajectory of a person as represented in this composite form to understand whether they're improving or whether, for example, if they're post-operative, whether they're getting worse and that sort of thing. We have an open SDK available for the Halo system. It's available at this address, and it includes a fair bit of documentation so you can actually pipe in your own data. And on the SDK page as well, although we're going through a lot of changes with regard to that, we also have a live stock market visualization that in Halo form visualizes stock market data per stock, so every stock gets a Halo. That's only available when the markets are open in the US as well. The second project I'm going to show you is entirely different. It's got multiple purposes, but one of the main purposes is to address what Halo doesn't address, which is if you have a particular type of data that has a very particular type of quality, how do you choose how to visualize it? And this is the job of the designer. I'm an artist and designer. And it's one of those things that most people do intuitively. So even if you're not well-versed in doing this, what ends up happening is that people just throw shit together and they're like, yeah, that kind of looks okay. And then they, of course, try multiple combinations, so it's trial and error as well. One of the aspects that I try to do with this is to determine if there's a truly objective way of doing that. So if you have particular types of data, is there a neurological basis that we can develop, and is there a methodology that we can develop that allows you to say it should be visualized in this way using these types of forms? The second aspect of this project is that what I wanted to do was to develop a means of creating automatic art. So it's essentially, I, as a creative, spend 99% of my day making these creative choices that feel intuitively right to me, but at the same time, too, wouldn't it be interesting if there's a way to develop a methodology of creating something that's considered quote-unquote art or design or whatever, that is purely automatic, that is driven by fundamental biological processes. So that's the second aspect. And then the third aspect is that this is a music visualization project. So what I wanted to do is to essentially visualize the emotional music listening experience. So what this requires then is to develop a methodology, to develop a model system that allows you to be able to do all these things that I just said. And really the only way to do this is to tap into the neurological basis of essentially being human. And one of the best model systems we have to understand how we experience the world with regard to what information comes in and how we process it is synesthesia. I'm sure a lot of you have already heard of synesthesia. If you haven't, synesthesia in pop culture parlance is essentially referred to as a crossover of senses. So synesthetes, essentially, chromesthesia is probably the most cliched version where you listen to music and then you see colors. But it's this term crossover that it's a misnomer because it implies that synesthetes have some sort of screwed up neurology, so that there's some sort of cross-wiring with regard to the signals coming through. Synesthesia is better termed ideesthesia. It's a really shit word, but it's actually the term that's used. Synesthesia is no longer used anymore. But in that word is imbued a really great concept, because the fundamental mechanism that is believed to be at play here is actually quite fascinating. So what essentially happens is that a signal input comes in, you hear music, a portion of your brain that's responsible for processing music processes the music, and then a separate portion of your brain, literally a physically separate portion of your brain, creates a neurological metaphor of the original stimulus input and also of the original stimulus processing. And this is what's actually quite interesting about it, because unlike cross-wiring, which is actually just way too simple, this neurological metaphor creation is essentially believed to be the basis of all human-to-human empathic communication. So we all do this on one level or another. It's just synesthetes do it on a very pronounced level that it can actually be characterized. The other cool aspect about this is that this is also the fundamental basis from which all metaphors are created. Now, in culture, we develop very complex metaphors based on history and whatnot, but their fundamental basis is this kind of system, essentially. And you'll see why. Synesthesia runs from ultra-extreme, such as mirror-touch synesthesia. This is my best slide, by the way, so it's all downhill from here. What's cool about mirror-touch synesthesia is that real pain felt by one individual is then felt as equivalent pain in a synesthete, so much so that people actually pass out from the pain. And it runs to the ultra-subtle, such as personification synesthesia, where among synesthetes, they apply a personality to abstract objects. So, for example, letters in the alphabet. Among synesthetes, people commonly feel that the letter U feels empty for obvious reasons. What's cool about this, though, is that there is a very high level of fidelity with regard to the personality that's applied to the particular abstract object. So the vast majority agree that the letter U feels empty. Although in this case, it's pretty obvious why. There are other instances where the abstraction is not so obvious. But you can see how this is where the fundamental basis of metaphors come into play, where we give abstractions a type of human personalities that we allow a level of communication beyond simply combinations of letters into words. So what I did is I essentially, because this is a music visualization project, I took a collection of 4 songs by the South London producer Burial, and what I did is I strung those together into a custom piece. The piece of music itself is actually relatively short. It's only 2.5 minutes long. But what's cool about Burial, if you're familiar with Burial, is that his music is highly emotive. So if you're going to use a stimulus response, a stimulus source, you should use something that has variability, of course. And then the other thing too is that there's a high variability with regard to frequency. So there are multiple frequencies at play, and they change very, very quickly. The reason the music piece, the composition, is relatively short, it's only 2.5 minutes, is that to complete this piece, and you'll understand why in a second, I had to perform a statistical analysis for every second of audio playback. To do this, then, on a neurological level, what's required is essentially measuring EEG responses. This is actually very easy to do these days. It used to be very difficult because you have to purchase extremely expensive hardware, but it's relatively easy to do these days because you can purchase things like this. Is the actual headset that I used. This is, I think it was made by Emotive. It was only $750 US. And what's cool about it is that it's entirely passive. You just simply wear the headset. It's not invasive, so you don't have to hurt anybody. And what it does is it measures your brain's response to any kind of stimulus, so be it music, be it what you see, smell, touch, etc., and that sort of thing. And typically, this is the EEG readout that you get. This is for 2 bands only. You get multiple bands at the same time. So there's a lot of noise that's extremely difficult to read, and without going into too much detail, there are a number of ways of going about this. One is to characterize it with regard to the emotionality that you're measuring. So typically what an EEG measures is engagement. That's one of the main axes. So is the person bored? Do they find the stimulus really exciting? And then if they are excited, is the excitement positive or negative? And then, of course, multiple combinations of that. And there are other axes as well. That's one way of characterizing. The other way of characterizing it is on a purely data level. So instead of filtering the data by understanding it from an emotional point of view, you just simply look at the data. In addition to that type of output, you can also use this type of output, which is a dynamic bar graph that occurs depending on the sampling frequency. I used 1 per second. So for every second, you get a 6-band readout, 6 bands here, and the bands simply just go up and down depending on the stimulus and how the person's reacting to the stimulus. So for the, I'll just show this. Oops. This is a real readout. So for the 2.5 minutes, I have a sampling rate of 1 per second, which that's for 6 seconds there. So you can imagine how much data that you get. This forms what I term the sequencer of the project itself. So this is the neurological response of the music alone. And it's like a lock and key system, essentially. So this is the lock. You have the pattern of the lock. And now you have to, if you want to visualize this, which is what I did, then you have to find a key whose pattern matches this lock. You're not looking for an overall key. That's impossible. That's ridiculous. What you're looking for is a composite system, a malleable, engineerable system where the pattern matches occur per second. And that's much more doable. Although, to be perfectly honest, I'll never do this again. So what I did is in a separate session, entirely devoid of any music, using the EEG headset, I exposed the test subject, which I forgot to mention was a 5-year-old boy, to very, very simple, well, I started with very, very simple colors, solid colors, blue, red, etc., and then measure the neurological response to those simple colors. The colors then transformed into gradients, and then the gradients were animated, all the while stepping up complexity to try to derive a system, not just simply flashes of types of visuals, but a system that's plastic enough where it elicits the same kind of emotional responses, at least in pieces, as the music did. Every time I explain this project, no one ever really gets it, but hopefully this time I really got it. And essentially, this is what you're going to find, is that if you can engineer and find a complex enough visual system, what you'll get, and this is an actual 1 second mismatch and mismatch that occurred, you'll get a situation where parts of the two, the music and the visuals, find a match. And so what often happens, of course, is that you'll find, you'll get 5 out of the 6 bands perfectly matching, and then 1 will be slightly off. And this is where the statistics come in, essentially. Analysis of variance to determine why, for example, in this case, the theta band was discordant. And the way to deal with this is to have a malleable enough visual system where you can assign to the visual system axes so that you can say, well, actually, it's because of axis number 2 that the theta band is not corresponding, and then adjust it. So that's why the whole point of the exercise is to have a system as opposed to just simply individual images that flash up on the screen. And the system that turned out to be the best as I was ramping up complexity over and over and over again is a computational floating dust system. This is the term that I've given it. All it is essentially it's like dynamic particles that move across the screen, but the system itself and the particles have a very particular behavior. Behaviors that can be characterized along 6 axes, and it's purely coincidental that Halo has primarily 6 axes as well. I think past a certain point, it becomes very difficult to characterize any kind of system as independent axes. And these axes are quite important. So size is the most obvious one. It's just simply the size of the particles, from extremely small, I think they were down to a pixel, to massive blobs. Color, full spectrum color, but for some reason, as I'll show you the video in a second, most of the colors tend to be relatively subdued, but that could be because of the original source input, the audio input. And what you'll also find when you see the video is that you will notice pronounced correlations between different axes. So size and color tend to be correlated. Speed is the speed of the, speed is the speed of the particles as they move across the field of vision. That's pretty obvious. You'll see a lot of speed variation in the video itself. Density is one of the most pronounced effects, and it's actually highly correlated with predictable aspects of the audio input. And it goes from extremely sparse, almost virtually nothing on screen, to extremely dense. Movement is just simply the concerted, whether or not there is concerted movement in the particle directionality. So you'll see this sweep from left to right. And then uniformity is the number of directions of movement, which gives you either a very calming directionality, kind of like fish in a river, or this kind of chaotic effect. Those are the main axes. The project itself was essentially a compositing exercise. So my role in this, and because the entire thing was passive and entirely data-driven, my role was essentially like biological CPU. So in addition to doing all of the statistical analyses, 1 per second, and then finding and adjusting for the visuals that are concordant with the music stimulus, 1 per second, it's essentially hundreds of different layers of the dust videos, essentially. Once this is done once, though, the reason I did it this way, as opposed to going back and regenerating the computational dust, is that I wanted it to be an absolutely faithful one-to-one representation based purely on data, based purely on statistics. But once this is done once, you can reprogram so that the computational dust is essentially just goes off on its own, which means it can be a live system. As long as someone's wearing a headset and experiencing any kind of stimulus, although a visual to visual is kind of weird. But for example, smell, we're building one now that's based on smell, or audio in particular. I think most people tend to be interested in this crossover between audio and visuals. And then the actual video itself, do we have sound? Sound? Well, I guess we'll find out. No, there's no sound. Is there sound? All right. And the actual video itself, you'll notice there are reoccurrent patterns that occur with regard to types of audio, frequencies, vocals, and then the responses that exist in the dust particle movements and behaviors. So the frequency of the vocals makes a big difference as well, particularly in density and directionality. And though there are at times predictable repeats that occur, there are other times there aren't. So it's actually not as predictably obvious as you'd expect. But that also depends on the person. How engaged are they? You know, if there are times, and the music was relatively short, but if it was long, a 5-year-old boy would probably get bored, and of course the EEG then is not registering anything of meaning. But again, an entirely passive system. There was absolutely no creative input on my part for this project at all. And again, it depends on the type of system that is generated, but another system that is also plastic enough could generate similar types of behaviors using entirely different visuals. Although it's very difficult to imagine what can be more plastic than simply particles on a screen itself. And as I said, the next step after this is to create a live version where the particle dynamic behaviors are entirely computationally driven live through live streams of EEG being shunted essentially into the system itself. Because then, once the statistics have been done once, that's basically it. Thanks for listening. Any questions?
Yep, we have time for any questions. From some of that animated discussion going on, then I think you've wowed them all. There's lots of hand waving going on. No questions. Aha, a gentleman over there.
Oh.
Hi, very interesting presentation. What would you say would be the application of the last part that you showed? You initially started off saying with kind of making art on an automatic programmed basis.
Yes.
But now what would be an application which you would apply this to? That I didn't quite follow. I could follow the Halo part, but the second part I could not.
It's essentially equivalent in that what Halo is doing in the iOS application that I showed you is taking sensor data, which is your personal biorhythm data, and it's representing it in Halo form, in visual structural form. EEG data is essentially an emotional transcription device. So if you can imagine, if it actually could be portable enough, although there are new EEG bands that are literally, they look like headbands, so they're not as complex as the one that I use, which is a slightly older model. But if that became mobile, what you can do then is create a visual transcription of your emotionality and how that varies across the day. And the reason that's interesting is that there was an experiment that was done recently. It was a really fascinating experiment, not using EEG because it's not really portable, it's not mobile yet, but they were using, there were wristbands that measured skin conductivity, although the EEG just measures variation in skin electricity, but that's correlated to your brain's response. But galvanic skin response is a really, I don't want to use the word cheap, but it's a cheap way of measuring emotionality. So what it does is it determines on a very coarse level your emotional response to a situation. So what this experiment did is they gave 20 architecture students these galvanic bands and had them walk around New York City and then just simply geo-track them wherever they went. Based on the geo-tracking, they knew the type of, and they coded the type of architecture, whether it's modern, Gothic, etc., neo-Gothic. And then they measured, and they went back into the lab and they measured and they mapped out the variation in the galvanic skin responses based on the type of architecture. And what they found was that people were not engaged with modern architecture. So what they were emotionally, mentally, neurologically engaged with Gothic architecture, visually complex architecture, and in particular Gothic architecture that was encompassing. So for example, when people went inside cathedrals, even if they're atheists. And so what they're able to do essentially is to track emotionality, but then track emotionality and then map it to how you live your life. So if you can take that even further and say, if you use something like EEG or galvanic skin response bracelets, and then you map out the interactions that you have with particular types of people, and then you notice that there's one prick that makes you feel like shit all your life. And then what you can do is structure your life from a meta-understanding perspective. So the last project is essentially that, is to try to develop a visual tool that is purely passive, that is expressive enough that it can be read. So although this is highly expressive, it can be focused so that it's more metricized, essentially, so that you can measure variation like you can with the Halo system. But imagine the Halo system plugged into an EEG, which is what we're doing next.
And I have one question regarding the Halo system. You started off saying that many people have difficulties reading an XY graph or a representation on a two-dimensional schematic.
Yes.
How easy or difficult do you think would it be to make Halo popular? I mean, it looks cool, but then to the practical purpose of understanding your health or activity level, or what are you doing right, what should you do, what should you be doing to make yourself into a better health situation? How easy or difficult do you think it would be?
Yeah, that's a very good question, because when we first started out, And I haven't showed you all the axes, but you can imagine how complex a system this is, and the difficult task of editing combinations of axes to say, well, you can put these two together, but you can't put this one into at the same time. That was the most difficult part. So with the rollout, the first rollout that we have, the halo that you're given is a halo that you have to grow. So you get a new halo every day, so you have to make a new halo every day. That repeat function allows you to learn the system. And so when you see it grow based on the type of things that you do, such as when you jog or when you run, and then it dynamically changes, there is an intimate connection between you and the halo's behavior. So what I didn't mention is the data granularity that comes in. So the heart rate information that comes in when you exercise is every 5 seconds, which means that with the halo, we're testing it now on a bunch of users, is that when you exercise, you actually watch the halo, and it changes while you exercise. And so what that does is, unlike individual graphs where you wouldn't necessarily do that in HK, actually I don't think anyone does that in HK, where they simply watch the graphs move, it creates a learning reinforcement, which I think we assume will mitigate some of the more complex aspects of understanding a multidimensional structure. But the big advantage, so yes, there is a cost to it. I mean, I'm sure there's a learning cost to it. But the big advantage is synthesis. So if you were to take those 4 or 5 axes that I just showed you in a very simplified halo for the Apple Watch, and if you put them into individual graphs, and if you presented that to a person versus a halo system, I'm like 99% sure that to be able to synthesize 5 different graphs is way more difficult than looking at the halo system.
Thank you.
Especially for the average person. I'm a statistician, so I mean, easier for me, but what can you say?
Any other questions?
Thank you. If I got it right, the analysis of the correlation between music and emotion is based on slices, second slices.
Yep.
But wouldn't this mean that you can take all the seconds of a song, shuffle it, and would have the same emotions in a different order, although it sounds horrible?
Yeah, you could do that. And actually with Barrio's music, you could probably do that and it would sound very similar because his music is highly dynamic. It changes quite often. But that was the point of using that source material because one, it's engagement. So variability kind of forces you into engagement. So the EEG, if you are bored, essentially doesn't measure anything other than the fact that you're not engaged. So you need a level of engagement in that the original source material has to be something interesting to you, which is why I used a 5-year-old child versus an adult, because an adult is already preconditioned to find things that they like or that they don't like. But yeah, you could shuffle it up because it is done in slices. It has to be done in slices from a tractability point of view. But then the original sound would sound kind of shitty. So.
I think it would not be music anymore.
No, it wouldn't. But yeah, once per second, it would sound quite odd. I never considered that. But yeah, you could do it.
Thank you.
So I think one last question, and then we
Just a
need
quick
to
one.
finish.
For the second project, is there any amount of random noise or randomly generated movement, or is every single dot essentially an interpreted signal from the brain?
Yes and no. So the amount, I'm sure there's a level of gray area with regard to, for example, density levels that could have been pulled, either scaled back or uplifted, that would have elicited the same neurological response for that particular segment. The reason instead of going back and reprogramming the computational dust so that it was purely data-driven on the second pass, so you have the music sequence, EEG sequence, and then after you've done all the statistics, you can reprogram the dust so that it just simply goes off on its own. The reason I didn't do that was to avoid noise. So what I wanted to do was a real true one-to-one. There was no interpretation. These particle and the segments is exactly what the child saw. But you can, that's the live version that that I was mentioning, is that if you go back and you say, well, I've got the sequence and I know how the computational dust should behave based on the statistics that I've already done, then you can reprogram the computational dust and then it can be purely live. But then that assumes that every single test subject is going to be responding to the same types of combination of visuals. I don't know if that's the case. I'm sure it's not. You know, an adult, I'm sure, responds differently to a child because they've been conditioned. So a child may find dancing dots really exciting and happy. An adult may, especially if a neurological adult, may find it really agitating. So you may not get the correspondence between the two.
Thank you.
Thank you very much, Peter.